Okay, so in this video, we are going to look at a few examples where, even on the surface, it looks like we may be able to apply L'Hopital's rule, and even in some cases, we will get the right answer using L'Hopital's rule. As we will see, it's not always the best idea. Let's look at a basic example. So, what if we consider the following limit? So the limit, as x goes to infinity, and I could make the example much worse, but I will start with a basic example. What if we have the limit of a ratio of two cubic polynomials as x goes to infinity? Suppose we have 4x cubed minus x squared plus 5x plus 1, so one cubic polynomial, over, say, 2x cubed plus 6x squared plus x plus 9. And we're letting x go to infinity. Sorry about that. And the question is now, what's the limit of this rational function as x goes to infinity? As always, we look at the type of case that we are facing. We know by now that when x goes to infinity, the dominant term takes over the smaller order terms. So as x goes to infinity, 4x cubed goes to infinity, 2x cubed also goes to infinity, so we'll have an infinity over infinity case. So on the surface here, we can use L'Hopital's rule. So let's here just apply L'Hopital's rule without too much thinking. Infinity over infinity case, we can use L'Hopital's rule. The limit stays the same, x still approaches infinity. And again, L'Hopital's rule says that if you are in the 0 over 0 case, or infinity over infinity, you replace each function, the numerator and the denominator, by the respective derivative. Differentiate the numerator, you'll have 12x squared minus 2x plus 5 over the derivative of the denominator, which will give you 6x squared plus 12x plus 1. We can simplify this, so we look at the case that we are in. And once again, the dominant term on top and on the bottom is x squared. As x goes to infinity, both of these go to infinity, and we have once again an indeterminate case, but of the form infinity over infinity. So we can once again apply L'Hopital's rule. X still approaches infinity. Replace the numerator by its derivative, so you'll get now 24x minus 2 over the derivative of the denominator, 12x plus 12. If you wanted to, you could factor a 12 and a 2, but you'll see let's not bother with this now. And again, we have a rational function, and as x goes to infinity, the dominant terms top and bottom are 24x and 12x. Both go to positive infinity, so we get positive over positive infinity case. Once again, in indeterminate form, we can use L'Hopital's rule again. X still approaches infinity. Replacing the numerator by its derivative, which is simply 24, the denominator by its derivative, which is 12. And now we are asking what happens to 24 over 12, which we know is 2. As x goes to infinity, well, as x goes to infinity, 2 is always 2. So the answer is simply 2. So if we go back, the original limit of this ratio of two polynomials as x goes to infinity is equal to 2. And it took us 3 applications of L'Hopital's rule. Let's go back now and solve this problem without using L'Hopital's rule and show that it really just takes one line and not all of this work. So we have the limit as x goes to infinity it was 4x cubed minus x squared plus 5x plus 1 over 2x cubed plus 6x squared plus x plus 9. As we said before, we have here an infinity over infinity case, and now we say forget L'Hopital's rule. We know how to handle cases like this. All we have to do is divide the top and the bottom of our fraction by the largest power of x, and that is 3. X cubed is the dominant term on top and on the bottom of this fraction, so we multiply top and bottom by 1 over x cubed. Because 1 over x cubed over itself is just 1, let's multiply through top and bottom by 1 over x cubed. So what are we going to get? Well, 4 minus 1 over x plus 5 over x squared plus 1 over x cubed. That's our numerator, over 2 plus 6 over x plus 1 over x squared plus 9 over x cubed. And if you look at all these terms, 1 over x, 5 over x squared, 1 over x cubed, 6 over x, 1 over x squared, 9 over x cubed, as x goes to infinity, each one of these 6 gives you a constant over infinity. So they both, not both, but they all shrink to 0. And we were left in the end with a ratio of 4 over 2, which we know is equal to 2, as we had obtained with L'Hopital's rule. But look at how much slicker this is, right? This is really, really slick. We had the limit, infinity over infinity, multiply top and bottom by 1 over the dominant term, the largest power of x, one line, and we get to the answer. Whereas with L'Hopital's rule, it was quite a bit of work. And I was nice here, I only gave you a ratio of 2 cubic polynomials. What if I had given you a degree 10 polynomials on top and on the bottom? You see, for a degree 3 polynomial, top and bottom, you have to apply L'Hopital's rule 3 times. If the degree on top and on the bottom were complete polynomials of degree 10, you'd have to apply L'Hopital's rule possibly 10 times. If it were of degree 100, and you had terms from x to the 100 all the way down to a constant, you'd have to use L'Hopital's rule 100 times. But now if you look at the idea of dividing top and bottom by the largest power of x, whether you have a degree 3 polynomial, 4, 5, 6, and beyond, or 1,000, it will always be one line. Single out the largest power of x, divide top and bottom by it, multiply across, every term will shrink to 0 other than the multiple of the dominant term on top and on the bottom. So this is one really, really big class of limits, ratio of polynomials, where in essence one should never ever bother using L'Hopital's rule, because dividing top and bottom by the greatest power of x will always produce a one-line solution, whereas with L'Hopital's rule, as the degree increases, the odds are that you'll have to apply L'Hopital's rule a greater number of times. So this solution becomes less and less efficient. That's one example where, with a ratio of 2 polynomials, x going to positive or negative infinity, one should never use L'Hopital's rule, but using this technique. Let's look at one other example that is even more dramatic. With a ratio of polynomials, x going to positive or negative infinity, L'Hopital's rule will always yield the answer, except in too many steps. This is too much work. Let's consider one example where L'Hopital's rule actually goes in circles forever. This will be our second example of this video, and actually our last one as well. So, what if we consider again x approaching infinity, taking the root of x squared plus 1 over simply x. As always, we look at what kind of case we have. Well, as x goes to infinity, the root of x squared plus 1 also goes to infinity. Same thing for x. So we have, once again, an infinity over infinity case. So it looks like we may be able to use L'Hopital's rule. Well, let's see. We are applying L'Hopital's rule. And again, we replace the top by its derivative, the bottom by its derivative. So let's see here. Root of x squared plus 1, that's just x squared plus 1 to the power of 1/2. And we have to differentiate this with respect to x. The outside function is the power of 1/2. By the power rule, we bring 1/2 down. Subtract 1 from 1/2, you get negative 1/2. Times the derivative of the inside, x squared plus 1, the derivative of this is 2x. You can cancel the 1/2 with the 2. Now if you leave the x on top, and you sand this term on the denominator, the power of negative 1/2 becomes a positive 1/2, power of x squared plus 1, but a positive 1/2 power is just a square root. So the derivative of the numerator, root of x squared plus 1, is simply x over the root of x squared plus 1. So x over the root of x squared plus 1. Now L'Hopital's rule would say the derivative of the top divided by the derivative of the bottom. But the derivative of x is 1, so if you divide this by 1, you get the expression back. And if you notice, something is kind of interesting. What's happened here? The numerator ended up being the denominator, and the denominator ended up being the numerator. Right there, it's looking kind of odd. Let's apply L'Hopital's rule, or see if we can apply it one more time. The answer is yes, because as x goes to infinity, we already know that these two terms both go to infinity. So let's apply L'Hopital's rule one more time. The top will be replaced by its derivative, which is 1 over the derivative of the denominator, which we have previously found. It's just x over the root of x squared plus 1. Well, the limit stays the same. If you do 1 over a fraction, you get the reciprocal, therefore root of x squared plus 1 over x. And this looks rather familiar. Look at the original limit. Root of x squared plus 1 over x as x goes to infinity. Root of x squared plus 1 over x as x goes to infinity. We are right back to where we started. We had this limit problem, infinity over infinity. Apply L'Hopital's rule once. We got a slightly different limit. Still an infinity over infinity case. We apply L'Hopital's rule one more time, and we get right back to where we started. And you see that we will loop the original limit forever. Apply L'Hopital's rule again, you're right back here. One more time, you're right back here. One more time here, one more time here, and you'll go back and forth between this limit and this one forever. So L'Hopital's rule here fails miserably. You'll never get to a different limit than this one or this one. In both cases, you get infinity over infinity, so you're stuck. Well, let's look at now how we should have solved this problem really easily with that L'Hopital's rule. This was the limit, x approaching infinity, positive infinity, of the square root of x squared plus 1 over x. We know that this gives us an infinity over infinity case, but again, we have a square root of a polynomial over a polynomial. We can simply divide as we did in the previous problem, top and bottom by the greatest power of x. Single out the x on the bottom, and you can do 1 over x over 1 over x. if you hope to get rid of the square root here, you'll have to replace x by the root of x squared. Since x approaches positive infinity, x is positive, and so 1 over x is the same as 1 over the root of x squared. And if you multiply x by 1 over x, all you get is 1. So in the end, you're left with the limit, as x goes to infinity, of, well, the square root of this times 1 over that, so just the root of x squared plus 1 over the root of x squared, which you can combine because root of a over b, as you know, is the square root of a over b. So combine this square root over this one as a single square root, being x squared plus 1 over x squared. Divide both terms in the square root by x squared, so x squared over x squared is 1, plus 1 over x squared, 1 over x squared. But as x goes to infinity, so does x squared, and so if x squared goes to infinity, 1 over x squared will go to 0. And you're left in the end with the square root of 1, which is quite simply 1. And there you have it. So you see that this limit was actually a very standard limit problem. Divide top and bottom by the largest power of x. One trick replacing x by the root of x squared because x was positive. Simplify the argument of the square root, and the limit is 1. So you see, with L'Hopital's rule, this limit was going nowhere. And it's not even like it would be a lot of work. It would literally never, with L'Hopital's rule, give us the answer. We've tackled this problem with a classical technique and found the answer in 2 lines. So this is really the lesson of this video. If you can tackle a problem, a limit problem, without using L'Hopital's rule, that won't require you too much work, so a classical limit, you should do it using a classical technique and not use L'Hopital's rule. Only use L'Hopital's rule if in 2 cases, the limit you have absolutely no tools that would allow you to solve the limit, or if you get a feeling that maybe with L'Hopital's rule, you may get a simpler, shorter solution. But if you can tackle the limit directly without using L'Hopital's rule, you should try to avoid it. Especially if what you have is a classical problem, such as the 2 examples that we have looked at in this video.